everyone. Welcome to our second episode of Anatomy, and today we're going to be discussing
Action
action
potential.
potentials.
Ooh, so these are really cool because they're how neurons transmit information. We talked a little bit about this in the first episode, but it's a property called excitability,
hmm
that electrical activity. Mm-hmm.
So we have a little visual here, right?
Yes, so you might think, wow, that's just one cat. But
Mhm.
wait, there's another cat, and there's another cat.
Oh yes, I was wondering this earlier. So what do the mice represent?
Well, so I like to think about it like the cat is the initial start of the action potential, right? And the
hmm
mouse is going to be the next one. So it's like jumping to go get the mouse. The mouse is kind of like the nose of
Oh.
reindeer because it's going to jump along these little cool nodes here. We'll get more into that later.
hmm
But this is also cool because it shows the direction of the action potential is always from the soma to the axon terminals.
Wow, that's so cool. I'm excited to jump into today's topic, so let's keep going. Ooh, what do we have here?
So this is a neuron. This is a neuron in the central nervous system, and you can tell that by the oligodendrocyte here. We'll talk more about that in the future. But it's pretty boring until we do this to
hmm
label the dendrites there and the axon terminals over here. So we talked about this in the last one. This is just to remind you like the flow of information. You
hmm
have this arrow. Everything always goes from dendrites to axon terminals. And that would be the flow of information or the action potential.
Yeah. hmm
Okay,
Wow.
so this looks incredibly complicated, but this
Mhm.
is going to be your resting neuron, right?
Yeah.
So what I will start with is just talking about what all these weird dots mean. So first, the pink is sodium. And what I want to point out here is there's a lot more sodium outside than inside. And remember, sodium is positively charged.
hmm
And then the next one we're going to look at is potassium. And Kate, what do you notice about the green potassium?
Um, it's more concentrated inside the cell compared to outside.
Yes. So this is what's going to contribute a lot to this that red thing. We'll see that later. That's the sodium
hmm
potassium pump. That's super important. And it will also contribute to this charge that's always around there. But first, we have to talk about this, which,
Right.
yeah, and where are the chloride?
They're all inside the cell too.
Uh-huh.
hmm
So since chloride is negatively charged, and you also have these like purple negatively charged proteins, those are large proteins, and they're only inside the cell. The inside of your cell is going to have a negative charge, which means the
hmm
outside is going to have a positive charge relative to that. So that's called the resting membrane potential, and it sits at around negative 70 millivolts usually.
hmm
And this is maintained because, well, actually, we'll get more into that later. So let's take a quick look at this. So notice how you have so much more potassium inside and not a lot
hmm
outside. So you have these cool things called potassium leak channels. And if they're open, Kate, where do you think the potassium's going to go?
Outside of the cell
Yes. And
because of the membrane potential, right?
because um you're there's a big concentration gradient of the potassium. It's not really driven by an electrochemical gradient. That's driven by something else that we'll talk about later.
hmm
But the potassium going out is going to give the inside an even more negative charge because you have positive leaving. And remember,
hmm
voltage is the charge of one thing relative to another. So since the outside is gaining even more positive charges and the inside is losing positive charges, it's going to make the voltage even more negative.
Yep.
Okay, do you want to give it another click?
Sure.
Okay, so we talked about this a little bit earlier called the sodium potassium pump.
Yes.
And this will basically be what maintains the resting membrane potential. So,
hmm
what do you notice about this one?
Um, so this requires energy, right?
It does. That's why it's called an ATPase. So, you'll see that one ATP is used to pump three sodium out and two
hmm
potassium in.
Wow.
Now, this is what is going to give you this gradient we talked about before, because you have to,
hmm
since we said potassium's really its gradient and wants to flow out of the cell. In order to put it into the cell, you need that ATP, that energy. And also it's the same for sodium. It's got a lower concentration inside and a higher concentration outside, so it is going to take energy to pump that out. But this is super important. It's found in all of your neurons. It's also found in other tissues, but it's super important here, and that's what gives it the gradients that set up the entire neuron physiology.
Wow. Wait, one question actually.
Mhm.
I read somewhere that like there's more permeability for K plus ions. So can you explain a little bit of that?
Yeah.
Mhm.
So basically, you see how we don't have any sodium channels on here yet, right? There's no
Mm-hmm.
ones in pink.
Yeah.
We do have more potassium leak channels. So that's the permeability they're talking about.
Oh.
And basically, that's just so that you have some potassium to pump back in, right?
Wow.
Because sodium has a really intense concentration gradient, right?
Mhm.
So that's that's less of a problem because it's already very concentrated. But yeah, the permeability to potassium is just these leak channels that help to establish the charge and the ion gradients.
That is so cool.
Okay,
Thank you so much.
of course. And so we talked about it a little bit before. It's going to maintain at negative 70 millivolts, and that's called
Hmm.
the membrane potential, the resting membrane potential.
Yes.
Okay.
Wow, my favorite glutamate.
Great. But we'll get to GABA next. That's even better.
Ooh, oh yeah.
So for this one, we're going to be looking at what's called an excitatory postsynaptic membrane potential, which sounds incredibly complicated, but it basically just means that we're exciting this neuron, this cell here.
Yeah.
So we're going to act like this is a dendrite,
Mhm.
and this is we're in a little synapse. Maybe there's a cell over here. So in our dendrite, we have obviously the positive and the negative, that's the resting potential. We also have this thing called an AMPA receptor. And so that AMPA receptor is going to bind to glutamate, and it's going to cause the gate to go down.
Uh-huh.
Isn't
Whoa.
that visual?
Wow.
And basically, this is called a ligand-gated sodium channel.
Hmm.
So it sounds really complicated. What is a ligand, Kate?
Isn't it like a protein binding receptor on the cell membrane?
Yeah, so a ligand is going to bind to a receptor. It's just the thing that binds to the receptor. So
Oh,
you
okay.
have voltage sodium
Uh-huh.
channels, which are important later, but the ligand ones are the ones that neurotransmitters bind to, and they
Hmm.
open so that our sodium can flow in, and that pink sodium.
Wow.
So, Kate, if a bunch of sodium is flowing in, what do you think is going to happen to the inside of the cell in terms of charge?
It depolarizes.
Yeah, and in terms of, is it going to be more positive, more
Hmm.
negative?
It's more positive.
Yeah, because obviously you're bringing in so many positive charges from the sodium.
Hmm.
So that's sodium in, and it's going to make the inside more positive.
Wow. Oh, sorry.
And then our EPSP is going to travel down the dendrite to the soma, to the axon hillock, which we'll talk about a little bit later. And that's just the direction of flow.
Hmm.
Okay. And
GABA.
GABA.
GABA, GABA, GABA.
What's so cool about GABA? What is its main function in this CNS?
It blocks the signals.
Yeah, so it's inhibitory, right?
Hmm.
And GABA is super important for things like epilepsy, because if you're not
Oh.
inhibiting things, then
Hmm.
everything's going crazy and you get seizures.
Oh no.
Uh-huh. So what we are going to look at here is called an IPSP, or an
Hmm.
inhibitory postsynaptic membrane potential. Okay, so if we look at this cell here, it's obviously got the resting membrane potential,
Hmm.
but also it's got these two green dots inside, and it's even more negative.
Ooh.
So that's a cool effect of GABA binding to this GABA receptor. This is specifically a GABA A receptor. GABA B receptors also do something similar, but not necessarily this. So we'll have GABA binding to that. The gate goes down, and we get these cool ions going in. So these are
Ooh.
chloride ions, and they are
Hmm.
negative. So makes the inside more negative.
Hmm.
So that's the opposite of glutamate.
Wow.
Hmm And that's going to make this one negative. And yep, that's the chloride going in, more negative, and it's going to go down to the soma. Okay, so what do you know about the axon hillock?
It integrates the IPSPs and the EPSPs,
Oh yeah.
and it's the decision point for action potentials.
Uh-huh. So the axon hillock is where summation happens, and we talked a little bit about this in the last episode. Basically, you've got your EPSPs, and you're going to add to those your IPSPs.
Oh.
So remember, EPSP excitatory, IPSP inhibitory. And we're going to see is that greater than negative 55 millivolts. Now, what's so special about negative 55 millivolts?
Isn't it like an all or nothing?
Yeah.
Uh-huh.
So the negative 55 is the threshold potential.
Threshold, yes.
So if you're greater than this, action potential. If you're less than this, no action potential. That's the all or nothing. It's really important. There's no like half action potential. No. Yes or no. And this happens because there's these cool voltage-gated sodium channels. So since this one is greater than the threshold potential, you are going to get an action potential. And when it hits negative 55 millivolts, these voltage-gated ones, they only open when it's negative 55 or less, or more, I should say, are going to open sodium influx. And you're going to get what you saw in the EPSP with sodium influx. And we'll go more about that in a sec. And that's the direction of the action potential, obviously, just again.
Nice.
Okay. So, Kate, do you want to do a little bit of explaining on this one with the sodium influx?
So I know that the ion channels for sodium open first,
Yeah.
and that causes the influx of the sodium ions into the cell membrane.
Yeah.
Yes.
And it's going to make the inside more positive. So Kate referred to this earlier as depolarization,
Yes,
which
depolarization.
that's how you'll often see it described in tests. Sodium influx makes it positive, and then it's going to travel down, down, down. We'll pretend this is the next node of Ranvier, right? Or not, this isn't the next one, but it would go on to the next node of Ranvier.
Yeah.
And it's going to only travel in one direction for a reason we'll talk about later. But at a certain point, these channels, they're going to close. They're going to have this cool little inactivation gate put in after about a millisecond. And then you move on to this. So Kate, do you want to explain the potassium efflux?
Yep. So after the sodium ion channels close, the potassium ion channels open. And this means that the potassium ions are flowing out of the cell. So this is called repolarization. And I usually get this mixed up with hyperpolarization a lot, but isn't it because like hyperpolarization occurs because the K plus channels are slow to close?
Yes, exactly. So what Kate mentioned is great because the sodium channels are really quick to stop so that like we'll talk about later so it can't flow backwards. The potassium channels take longer because it needs to get the whole gradient reestablished. And it needs to do that while that poor sodium potassium ATPase is working overtime to get it all back to normal. So these have to take a little longer. And repolarization and hyperpolarization are really cool, right? So since these are open for so long, you're going to get a bunch of potassium flowing out, and that makes the inside even more negative than it usually is. So it can drop to like negative 85 usually. It'll go back up once the sodium potassium ATPase does its work. But yeah, it will hyperpolarize during repolarization phase.
Yep. Thank you so much.
We good? Okay, next one.
Alrighty.
So, what we're going to talk about here are just some of the refractory period mechanics. So, right here we see in purple our voltage-gated sodium channel. And what's in the middle of that?
A little inactivation gate.
Yeah. So that's what we talked about before with you have your lovely open channel, and then after about a millisecond it's going to close so no more sodium can flow in. And that stops the inside from becoming more positive, which is basically like so if we look at the image from before, kind of, the sodium's going to flow to the right, to the next node of Ranvier. But if this gate is closed, it can't open again for until another action potential is generated. And that's why it's called the absolute refractory period, because no action potential can be generated when this gate is closed. And it takes a while to open back up.
Yeah.
Um, and then we also have this one, which goes along with the hyperpolarization.
Mm-hmm.
And it's basically like all the potassium flowed out. So we're in that hyperpolarized state that Kate talked about.
Mm-hmm.
And it makes it so much more negative. It's kind of like an IPSP.
Wow.
And it makes it just a lot harder to start one. So you can have an action potential in the relative refractory period, but it's going to be a lot harder. You're going to need more stimuli.
Mm-hmm.
Anything else?
I think I'm good, thank you.
Okay.
Wow. I understand a lot more now.
Okay. So I like this graph because I see it so much on every single test I take. So do
Mhm.
you want to point out some key places on here?
Yeah, as Beatrice talked about, we started off with the resting potential at negative 70 millivolts, and then we have to reach that threshold potential of negative 55 millivolts, and it's all or nothing, or the action potential cannot be released.
Mm-hmm.
And then we get to the point where the ion channel is open, and then the sodium rushes in, and that's called depolarization, and that's around is it 30? Is it
Yeah,
30
30 to
millivolts?
40
30 to 40 volts.
positive. Mm-hmm.
Positive. And then afterwards, the sodium ion channels close, and then the potassium ion channels open. This means the potassium ions rush out of the channel, and this causes repolarization
Mm-hmm.
and hyperpolarization as well.
Yeah, so what's labeled on the diagram is like repolarization is the whole stage from about -3 to 4, where it's going
Mm-hmm.
to normal. Actually, 2 to 4.
Yep.
Um, but this point specifically is the hyperpolarized point because it's the lowest and you see it dropped a little bit below the resting potential. So, like, I kind of like to look at this here. Between resting and threshold, that's all your ligand-gated channels. And that could be inhibitory ones or excitatory ones. It's just as
Mm-hmm.
long as there's more excitatory than inhibitory and it reaches -55, you're good to have an action potential. And
Yep.
then from threshold to depolarized, what opens then, Kate?
The sodium channels.
Yeah, the voltage-gated sodium ones.
Mhm.
And then from depolarized, all the way up until you're back at -70, that's your potassium channels.
Yep.
Okay,
That's about it for
that's
this
about it.
episode.
Yeah. So, any questions?
I think you answered all of them.
Great.
Thank you for tuning in and wait for the next episode to be released.
Thank you.
Thank you. Yes.